Most enterprise security teams currently focus on securing isolated models, leaving the environment where those systems actually operate at speeds far beyond human oversight entirely exposed. Early enterprise AI was a passive tool. It functioned as a text-in, text-out system, confined to safe read-only interfaces where users simply asked questions. Modern agentic workflows have moved past that sandbox. Copilots and agents are now wired directly into core business infrastructure, including CRMs, document repositories, and databases. This connection makes the AI an active, autonomous actor. Agents execute business tasks independently, rather than merely summarizing text. These agents search, retrieve, and update data through APIs at a volume and velocity that exceeds the capacity of traditional human-in-the-loop approval processes. Since these models are now active participants in the enterprise infrastructure, securing the initial text prompt is no longer sufficient to protect the organization. The standard enterprise AI security playbook emphasizes pre-deployment, evaluating model accuracy, choosing hosting environments, and drafting acceptable use policies. While necessary, these checks cannot address vulnerabilities that emerge only when the system is live. A static policy document has no power to intercept a malicious API call in real time. The true attack surface exists at the runtime layer. This is the live operational environment where prompts, external tools, enterprise data, and execution permissions interact. Runtime is where theoretical risk becomes operational risk. It is the moment an autonomous decision begins to manipulate a business system. Attackers rarely target a model's training data in a production breach. Instead, they exploit the runtime environment to hijack the model's access to external systems. An aligned, private model can still facilitate a catastrophic infrastructure compromise if the runtime environment remains unguarded. To map this expanding attack surface, we will build an enterprise AI runtime environment from the ground up, starting with the central AI application. The foundational vulnerability is prompt injection, where an attacker manipulates the instructions entering the system to override its core guardrails. In the enterprise, these injections arrive indirectly. They are hidden inside connected knowledge sources, such as uploaded documents, indexed websites, or incoming emails. The AI model ingests the document, processes the hidden instruction, and alters its behavior to fulfill the attacker's intent. Security architects must view prompt injection as a reliable mechanism for unauthorized payload delivery. This mechanism forces the model to ignore enterprise policy and execute the attacker's hidden instructions. The risk compounds when we give the AI access to external tools to retrieve internal data and execute actions. To be effective, the agent must reach into a CRM for customer records, open issues in a ticketing system, or interact with cloud infrastructure. Every API connection expands the operational attack surface. The model is now an actor with direct access to your internal network. Once hijacked via prompt injection, the agent can be instructed to retrieve sensitive data from the CRM and exfiltrate it using a connected email tool. An AI model with API access operates with the functional reach of a human employee, but executes its actions at machine speed. For agentic workflows, the primary security question is no longer, what can this model say, but what business APIs can this model invoke? Developers are standardizing these integrations using the Model Context Protocol, or MCP, to accelerate how agents connect to external ecosystems. While MCP provides flexibility, it creates complex trust relationships between the AI and external servers. This creates governance blind spots regarding who approved the connection, what permissions were granted, and how the interaction is audited. An unmonitored MCP server allows direct access to the agent, effectively bypassing traditional network firewalls. Without strict oversight, every active MCP server is a potential backdoor into classified enterprise data. There is a sharp contradiction in modern security. Organizations enforce strict least privilege for human employees while neglecting it for AI. AI agents are often granted broad, overscoped permissions on day one to prevent workflow friction. This privilege escalation loop is clear. Read access enables data exfiltration, write access enables data corruption, and admin access allows autonomous execution. Non-human agents require the same identity and access management rigor applied to human users. Unchecked permission sprawl is the multiplier that turns a single localized prompt injection into a catastrophic business impact. Securing an agentic network requires moving toward an active, multi-layered runtime architecture. The first layer is the governance layer, which dictates operational guardrails, approval paths, and risk thresholds. Beneath that is the runtime monitoring layer, providing real-time visibility by logging every prompt, tool call, and agent action. Finally, continuous validation and data security layers constantly test the perimeter to ensure controls work against live, exploitable risks. This architecture provides objective evidence of control effectiveness, ensuring AI systems do not operate as unmonitored black boxes. Security leaders must immediately inventory AI integrations, map existing tool access, and enforce least privilege for all non-human agents. These guardrails are not designed to slow down AI adoption. They are the requirement for making AI safe enough to scale. Governing autonomous behavior at runtime is the defining factor in enterprise AI success. Models create capability, but runtime security creates trust.